Hi folks. I wanted to do a little bit of a tutorial on SOPs and DOPs because this is something I've always found a little bit difficult to wrap my head around, and I've never really found tutorials that quite covered what I wanted, so I figured I'd give it a go. And I'm going to cover two pretty trivial examples, I think, just to show you the general workflow and how you can use this in your projects. So the first is going to be a basic sort of generating geometry and constraints on the fly. So I'm going to show you just this basic example where you add geometry every few frames and you add a random constraint with it, and the simulation will adapt to that. So you'll get something kind of like this, which is in and of itself not that useful, but should show you some good mix of workflow. The other thing I'm going to show you is basically spawning in multiple copies of fractured geometry. And so if you have geometry with fracturing, that's going to have all of its own constraints, and to spawn in multiple copies of that, you have to spawn in both the geometry and the constraints and do some sort of naming updating. So we'll get sort of a whole bunch of, sorry, that's still selected. Let's go back here. So we'll get a whole bunch of these little cubes that are all fractured the same way, and you can spawn them in and have them all interact properly and all have their constraints updating correctly. So let's get started, and we're going to build these from scratch here. So we'll start with the first example. We'll just make some geometry here. Call this one Constraints. And we'll dive in. So the first thing we're going to need is some basic geometry to work with here. So I'm just going to make a box. That should do just fine. This is probably bigger than I want, so I'm going to just transform that. Make it a little bit smaller. I'm doing this in a transform instead of in the uniform scale here, because if I want to swap out this geometry sometime later, then it's a lot easier to just sort of pipe it straight back in and not worry about that. So we've got our nice small cube. That should work just great. And the next thing we want to do, which will seem a little bit strange because we only have one piece, is we're actually going to assemble this. So I'm going to use this assemble node, and the reason I'm doing this is because I want this to be packed geometry. The bullet solver that we're going to use is going to behave a lot better if this is packed. So under the Assemble tab, we can go down here and check Create Packed Geometry. It doesn't really matter for this if we give it a name attribute or not, because we're going to have to handle that on our own. So if you toggle that, you'll see it'll sort of update here because it doesn't really respect the normals very much while it's packed, but if you go ahead and unpack, you'll see it looks, oops, I unpacked points. If we just unpack regularly here, you'll see it behaves nicely. So that's all still back in there. So it'll look like this while it's packed, but don't worry about that. And then all we need to do is just drop down a null because we're going to want to reference this a little bit later. And I'm just going to call this GeoSRC for geometry source. So that's all we need for that part. We're going to need some geometry, and we're also going to need some constraints. So I'm just going to drop down another null here. I'm going to call this con for constraints. And right now I'm going to leave this totally empty. I'm not going to attach anything to it because at the start of the simulation we don't have any constraints. So this is just basically a placeholder here. So that the nodes we're going to have to use have something to point to, but we actually don't start with any geometry. We're going to add all of that in DOPs. So without further ado, this is actually all we need to set up outside of DOPs. We're going to do everything pretty much inside. So let's just drop down a DOP network. Here we go. And we'll set ourselves up for a basic bullet sim, which is a pretty simple thing to set up from scratch here. I'm going to use the rigid body solver instead of the bullet solver. And the reason for that is rigid body gives you this nice third input here, which is the post-solve input. Bullet solver just gives you a variety of sort of attached data, and you can configure the rigid body by default. It'll be a bullet solver anyway, so I find it a little bit cleaner. So we're going to use that, and then we're going to need some packed geometry. So I'll just grab an RBD packed object here, and I'll pipe that into the Objects tab there. So we can point this right off the get-go right to our geometry source here. I apologize, I'm using Windows Game Media Recorder, whatever it is. It doesn't give me drop-downs, it won't show pop-ups. So basically, I've clicked on this little SOP path, and I'm navigating to that geo-source thing. So you can see here, OBJ under that constraints, and then our geo-source node. And you can see that little cube we had popped in here. So if we were to simulate this now, I mean, nothing at all would happen. We have no forces. We're not doing really anything else of any consequence. So that's fine, but we have this object in here at least. Now what we want to do is we're actually just going to go straight ahead and drop down a SOP solver. So what are we going to be doing here? The way to think about this, if you go to your RBD packed object, or if you just sort of click on really anything in the solver here, we have a bit of a different spreadsheet here. But this is just showing you essentially these are containers that have all kinds of data that the solver is going to care about, but they also have geometry. So if we go to this packed object here, find it down here, just unpack that, you see all sorts of different stuff. We have colliders, all of these other bits of data, but we have this one little spot here for geometry. And if you click on there, you get all the normal spreadsheets. We get our points, our vertices, our prims, detail, and you can see all of this information that Bullet is going to use to update the position of this sort of packed object here. So what the SOP solver is doing is basically saying, here in this RBD packed object, we have geometry. This SOP solver, it's a SOP context, it's going to output geometry. And what we're going to do is just take the output of this solver and replace this geometry over here with whatever comes out of this. And the most straightforward way to do that, and the way that it does it by default, is it just takes, at every frame, or sort of every time it sort of iterates, it takes whatever the geometry is currently in here, and it just replaces it with this. So you take the existing geometry, you do some transformation to it, and you put it back in. It's a lot like, it's basically identical to the SOP solver out in the SOP context. So what we'll do is we'll pipe it into the post solve here. And what that means is that basically every frame or every loop through this DOP network, the rigid body solver, the bullet solver, is going to do all of its work, figuring out collisions, figuring out velocity, all of those updates. And then at the end, the SOP solver is going to take whatever geometry is left, it's going to do whatever we tell it to, and it's going to pipe that back in, and the next time we loop through, it's going to start working on that geometry. So let's dive in here and take a look. You'll see the context for the SOP solvers is a little bit interesting. It basically gives us by default a few different imports here. So the basic one here is the current DOP geometry. So this is that geometry in the tab, and actually here it just shows us straight away. So this is just looking at that point that we had to begin with. It gives us a couple of sort of fetch records here that tell us about impacts when things collide with each other, other sorts of feedbacks. We won't be looking at that in this tutorial. And it'll also give us an object merge for the constraint geometry. And we don't have any right now, but this would be one way to pipe that in. Now, the problem we'll see, and even in this particular setup, we're going to have to sort of get ourselves around this, is that this whole network, even though we have all of these different inputs, we can only have one output. Ultimately, it's going to have to end at one node, and that node is what's going to feed back out this connector and replace the geometry on this RBD packed object. So that means we can't really change the sort of geometry and the constraints all at once inside this because we only get one output. We only get one thing happening at the end. But we're going to start in this context anyway, just to show you sort of the really basic workflow. So what we want to do is basically every so often we want to add a new one of these cubes into our simulation here. And so the typical shorthand for every so often is just to use a switch, and we'll basically say something like if the frame mod 10 is 1. So this just says every 10 frames we're going to do something. So if we're not doing it, we're just going to take the existing geometry and pass that straight on through. I'll just drop an output node here. But every time we hit sort of 1, 11, 21, and so on and so forth, we want to do something else. So we're going to do this branch here. Do something. So what is it that we want to do? Well, we want to add more of those cubes in here. So that's easy enough. We can just drop down an object merge here. And again, you're not going to see my pop-up window, but I'm just going to navigate back to that same geo source node that we made before. So here we are, object level, our constraints network, and that geo SRC. So this is just a single point, and it's got a name because we assembled it, and that's all we've got there. What we can do is merge this with the existing geometry. So now instead of a single point, if we just look at that original geometry, we just have one point. We're just taking this geometry and we're merging it in. And so now we end up with 2 points. And this will continue to go on. So on frame 21, we'll add another one, we'll have 3 of them, and we'll basically keep having extra geometry. So you can probably already guess some problems here, but let's just sort of run this and see what it'll do for us. And we'll see nothing at all, but you can see on the geometry here that these things are sort of stacking up. We're getting more and more and more of them. Unfortunately, they all have exactly the same position, which means it doesn't really know how to handle the collisions. It's not really going to do anything. It's also complaining about something extra here that we'll talk about in a minute. But let's deal with this position problem first. Fortunately, this is pretty darn straightforward. This assembled geometry is just represented by a single point. It has a position, a velocity, angular velocity, all sorts of other things, but we really just want to change the position. So let's just say when we spawn it, we're going to drop down an attribute wrangle. We're going to modify these point values. So let's just get that in line. And we're just going to raise it. Let's just say our y-coordinate will be 2. Now if we head back up, you'll see something a little bit funny about SOP solvers that's worth keeping in mind. You'll notice we've made a change, but this, our sort of status, our cache bar here is still blue. It still suggests that it's live and it's correct. Normally it would go orange after you change something to tell you, this is dirty, it needs to be resimmed. SOP solvers, because there's so many nested sort of loops and feedbacks, it just doesn't keep track of this nearly as well. What you'll generally want to do is just go back to 1, and then go into any of your objects and just find one of these creation frames, simulation frames, just toggle it on and off to basically force it to reset. That's kind of how I generally force things to just sort of start fresh because we've made a real change. So if we run this now, again, what we're going to see actually is that this one will stay here because that's where we started with it, and then we'll spawn a new one at frame 10 up here around 2, and then we won't see any other changes because everything else will sim there and we have no forces. But let's just see if that's what it does. And there it is. So there's our first one, and then all the others you can see all have this same y-coordinate, so they're just sitting on top of each other. So let's just make this a little bit easier to see. We'll drop down a ground plane here, just to have something to collide against, and we'll throw a gravity force in here. This first one starts colliding, so let's just give it the same offset. We'll just go into its initial data, and we'll just set its position, its y position up to 2. I prefer to do this here in the initial state instead of back here when we're setting up the geometry for a whole host of reasons, but it's generally nice to have your initial raw geometry basically as centered, as sort of kind of generic in its position as possible. This is especially good for things like constraints, so I would just recommend keeping this centered for your raw geometry and just deal with your offsets within DOPs. So we'll start with that offset. And so that's going to start up there. And then if we run it now, there we go. So we'll see every 10 frames, we're just dropping a new one in here. And they're all sort of just piling up here. They're all behaving independently, and that's all great. Okay, so that's working nicely. And you can see that that's pretty darn simple to do. Basically, all we do is we set up some kind of a switch that says when should we do something new. We could even do this every frame if we were feeling crazy. And if we're not doing anything new, we just pass through the existing geometry. And if we are, we're going to merge the existing geometry with some new piece. So we're, in this case, just bringing in a new copy of that. Now we can turn to this little flag here. So you can see we have a warning. This means that the simulation is not super upset. Probably this won't show up. I think this will be a menu that's coming up over top. But if you go over and check that out, you'll find an error, and it says object contains duplicate values for the name point attribute. And we can see that really easily in the spreadsheet here. If I just scroll over to our names, sure enough, they're all identical. And that makes sense because we just merged in this single piece of geometry we had out here. It's named piece 0. And so that means every time we bring a new one in, it's going to have that same name, piece 0, piece 0, piece 0. Now, when we don't have constraints, this doesn't particularly matter. It's giving us a warning, not an error, because it's not really causing any actual issues. Once we start to get into constraints, this isn't going to work anymore, because we have a constraint that's supposed to attach piece 0 to some other piece, and everything is called piece 0, then it doesn't know what to sort of assign that constraint to. So this is, again, a pretty easy solve. We're just going to go back into this same wrangle here, and we're just going to update that name. And what we'll say is we'll set our name. So this is an sat because it's a string. And we're going to use sprintf, a nice sort of C-type function. And we're just going to go %s dash %d. And these are going to be placeholders. %s is a placeholder for a string. %d is a placeholder for an integer. So we're just going to need to give it 2 of those. So let's give it its original name. And then we'll just give it the current frame. So we're only spawning one thing in each time. That means that the frame is always going to be unique. We'll always get a unique name here. So here, for example, you can see that if this was executing right now, we would get piece 0, 135. So again, we'll go back to the beginning. we'll just do this little toggle on, toggle off to reset everything. And if we run it, it'll look pretty much the same. In fact, it should look identical. Sure enough, it's all stacking up there, but you'll see we have no warning over here. And if we go to our names, you can see that they're each unique. So if I scroll this up, we have P0, P011, 21, 31, 41, and we also get a nice verification that this is happening when we expect, when it's sort of the frame modulo 10 is 1. Now, you might wonder why we don't get anything on frame 1, because 1 mod 10 is 1, so that should be happening. And the reason is this whole simulation gets created on frame 1, and if you look at this solver, we're not solving objects on the creation frame. By default, you don't. By default, the creation frame is sort of when you initialize things and bring them in. Now, if we did tick this on, what we would find is that, let me just refresh, on our very first frame, now we have two things, because we brought in that original geometry and we brought it in on frame 1. So what we could do instead is actually, instead of loading anything in this original RBD, we're just going to pull that out. We're basically going to say this is now a placeholder. It should be empty until we do anything else. And then it's only on this first frame that we do this solve, and we add in our first bit of geometry. So we get 0-1 here instead. This is sort of totally at your discretion, at your preference, but it doesn't mean everything gets treated the same way. You don't have this sort of initial geometry. And I kind of like to do everything within the solver, because then you don't have to remember, okay, what's my edge case for the very first one? You just have everything being created within that same solver following the same logic, and you don't have to kind of worry about your initial settings here. So that means all of this tab, all of this becomes irrelevant because it's all handled inside here. Okay, so we've got ourselves set up. We're generating a whole bunch of these cubes. We're creating a new one every handful of frames. What we want to do next is add some constraints between these. We want to kind of randomly generate some new constraints as we do this geometry. And this is where things get a little bit more complicated, and you start to have to take a slightly different approach to this default SOP solver here. So if we go back inside the SOP solver, you might remember, well, we have sort of an input for our constraints, so we can bring those in, and we can make some modifications to that. But again, we only get one output. So when we pipe this in here into this final solve, we only get one kind of geometry going back through. And what we basically need is to have two separate outputs. So the way I like to solve this is, instead of using this internal logic of the SOP solver, I'm going to actually generate a SOP network here. And so it starts to get really recursive here, but once you start to realize that you can do this and understand how to use this workflow, this recursion can become really powerful. You can have DOPs inside of SOPs, SOPs inside of DOPs, DOPs inside of those SOPs. You can kind of nest as far as you want to go. I wouldn't recommend going too far because you'll quickly lose track, but it's a reminder that DOPs is not just fully contained within SOPs. They're just different levels, and you can sort of partition and encapsulate these things over and over and over again to get the effects that you need. So what we're going to do in this SOPnet is we're just going to call this update geo and constraints. And the first thing I'm going to do is just show you how you can use this instead of this internal context. So in here, first I want to access my existing geometry, and I'm going to do this with an object merge. And what you can do is basically, I'll just type this out actually. So we're going to go back up a level until we get into DOPs, and then we want our RBD packed object here, and then we're going to go to geometry. Now if I just do this, it's going to complain. It's going to tell me, I don't really know what that is. We see this little flag here. And the reason is DOPS networks don't like the backslash. Once you're in the DOPS network, you actually have to use a colon. I don't know why. That's just how it's set up. So by the time we reach here, we've gotten sort of backslash, backslash. In fact, let's make this an absolute path just so we know what we're doing. So we'll go obj, constraints, and then into our DOPNet here. So once we hit the DOPNet, we switch to a colon, and then everything inside the DOPNet, we're using these slashes again. So if I do this, it's still giving me this warning. It's a different warning now. What this warning is saying now that there's nothing in here. Actually, no, it is upset. Why is it upset? Possibly I didn't. Oh, there we go. I don't know why I put the quotation marks around it. Okay. So here we go. Now we have this geometry, and you'll see if I put this slash back in here, it gets upset. It doesn't know what that is, and the error will say, invalid SOP specified. So it just doesn't recognize this. So once you hit the .NET, just replace that / with a colon, and everything will resolve correctly. So here we get the geometry as it stands. And so what we can do is just go right back in here and recycle all of this code, all of these nodes. So we'll just copy those back to this SOPNet and paste them in here. And now we're just going to pipe this stuff right back in. I'm going to swap that, and very importantly, I'm going to swap this switch, because right now it's saying on every frame except for the 10 mod 1, so 9 frames out of 10 we're going to add something. We want just that 10th frame, so we'll swap that, and there we go. So now this is doing exactly the same thing as we were doing in here, and so to get it into here, we're going to, instead of using its default, so if you just create a SOP solver, all of this default is going to be set up, except for this one that we toggled on. We're going to instead say use external SOP. And so this is telling this to basically, instead of doing the calculation inside this network, it's just going to grab a SOP from somewhere else. And so what we're going to do is we're going to replace this output with a null, because we're going to have multiple outputs here, and we're just going to call this geo updated. So now we can go back to here, to this SOP path, and we'll just navigate into that network. What did we call that? Geo updated. There we go. So we'll accept that. So that's coming from this SOP network here, which I gave a really long name, which is part of why this doesn't resolve so nicely. But now instead of doing anything inside here, so we can even just delete this just to prove the point, instead of doing anything inside here, it's all going to update inside this network. So now if we just go back and just make sure we're reset, it should do exactly what we saw before. So far we haven't changed anything, but what we've done is move into a different context. And the reason this is valuable is that within this same context, we can now update the constraints as well. So before we can do that, we probably need some constraints, because right now this doesn't even have a constraint solver. It's got nothing at all going on in it. So to do that, we'll just drop a constraint network. Just slide that right in there. And this network is going to be upset because, well, A, we don't have a constraint for it, and B, we're not sort of giving it a path to anything. So let's use a hard constraint. Ironically, this will give it a nice soft behavior. I'm going to put that in there, and I'm going to just switch this and call it hard because it's a little bit easier. Okay. Now, actually, it occurs to me, I made that null before. We don't even need it. We can do the same thing that we did with this RBD packed object. Just start with it empty, and we're just going to create the geometry for it. So we don't need to start it out with anything, really. We can just sort of create all of it on our own. So in fact, I'm just going to go back here and get rid of that entirely, because we're never going to reference that. Okay, so we'll go back in our DOP network. Now, just like our RBD object over here, if we unpack it, we have a geometry tab. We find our constraints under relationships. Here's our constraint network. Dive down, we have another constraint network, and finally we hit geometry. And so in the same way that this RBD patch object is really just a container with extra data and geometry, our constraint network is also a package that has a bunch of extra data and normal constraint geometry. And constraints are just lines. Every constraint network imaginable is just a collection of lines. It's 2 points. It has a name for each point, and then it has a whole bunch of properties. What kind of constraint is it? What's its strength? All sorts of things depending on the particular constraint. But every constraint is fundamentally just a line, and it's a line that connects 2 points. So that's easy enough to build. We can make that in SOPs really easily. So that's what we're going to do. I'm going to head back in here, and what we're going to do is first we're going to grab our constraint geometry. So over here, we did our object merge and we grabbed our current geometry from the RBD packed object. Now we're going to grab our constraint geometry. So we'll go object merge, and we're going to, again, I'll do the sort of full path instead of the relative, just so we can see what's going on here. Constraints, DOP network. I'm going to leave it as the / for the moment, just because it actually lets me navigate a little bit more easily. Actually, it doesn't for this one anyway. So let's just go to colon, relationships, constraint network 1, constraints, and geometry. That should be right. You can always sort of go back and just kind of take a look at what this path is. Constraint network 1, relationships, constraint network 1, constraints, geometry. Okay, so this should be fine. It's going to be upset because there's nothing in there, so it's saying invalid SOP. Again, that's just because there isn't actually anything in here. Otherwise, this should be fine. We'll see if I'm wrong in a minute. Okay, so what do we want to do with these constraints? Well, we're going to do something very similar. We only want to do something on these frames when we add something new. So we're not going to add any constraints except when we add a new object. So we want a new constraint for that new object. So we're going to use this same switch. I'm just going to copy that over, hold down Y to get my scissors and cut across, and we'll just give it an output here. And this is going to be con updated. So again, we're going to pipe it through unless we want to sort of do something else. So I'll just sort of drag off just so we remember, okay, we've got two things happening. And in exactly the same way that we piped a SOP solver into the post solve on our rigid body, we can do the same thing for our constraints network. So we can do a SOP solver here, and we can pipe this right into here. We'll remember to tick solve objects on creation frame because we're doing that over here. And we're going to again use external SOP. And we're going to point to this very same network, and we're going to use con updated. Now, if we were to run this now, it should run okay. It's not going to do anything because we didn't do anything in our separate branch. So it's going to leave that as empty geometry, but let's just make sure it doesn't break. Okay, we're good. So now we get to the interesting part. What do we actually want to do here? So in order to construct sort of a new constraint, what I'm going to do for the sort of simplest version is we're going to say, okay, we've got a new object. Let's just pick a random old object, and we'll put a constraint between those two. So that's all we're going to do. That means we need to know about the new object, and we need to know about the old objects, and we need to create a new line. So because we're creating something entirely new, we're not going to be iterating over any kind of geometry. That means we're going to do a detail wrangle. We're just going to apply this a single time. And what I'm going to do is I'm going to pipe in on the second input here, so index 1. So I'm going to pipe nothing in on 0 because we're not iterating over anything. Again, we're just going to create something totally new. So I'm going to bring in our new geometry on this input, and I'm going to grab our old geometry on our third input there. So inside here, what I want to do is basically create a constraint between this new object, which has its own new name, and some other object in this geometry over here. So what we'll do is first we want to know how many, we basically want to grab a random point from here. To do that, we want to know how many points are there, and we're going to use that in a random function. So let's just find out how many points we have. I'll just say int npts for num points, and we're just going to use the nPoints function. And we're going to point that to index 0, 1, 2 here. That's the input that's coming from the old geometry. So that'll tell us how many points we have in there. And then we'll just grab a random one of those. So let's just make ourselves a seed here. I like to do this separately just so I can kind of keep track of it. And I'm going to make the seed just the current frame. And I'll just add some noise to that. Let's say 83. Okay, so to pick a random point, I'm going to use this seed. I'm going to say rpt equals, and let's say random rseed. And what I like to do here, and this will look stupid and some people will sort of judge me for this, and that's completely fine. Random in its documentation generates a number from 0 to 1. If you use this in something like a multiply with a floor, it's usually going to work, but if the edge case actually exists that it can do both 0 and 1, you're going to have an edge case every so often that breaks it. So what I like to do is just multiply this by some pretty large number, and then just do modulo endpoints. So this guarantees I'm getting sort of, I should make this an integer, I'll just cast that. This guarantees I'm getting sort of a number that will be between 0 and endpoints minus 1. I'm never going to get an edge case, this will always work. So it's a little bit silly, it's a little bit of extra computation, but I think it's fine. And it lets me rest easy. Okay. Now, what we're going to want to do from here, I'm going to save a problem that you may have seen already for just a minute. But first we'll kind of move on from here. So we've got our random point here. So now we basically have everything that we need to get our line. So let's just call this point A is going to be the point that's our new point. So we're going to get its position. I'll call that pose A. And we're just going to grab a point attribute from the first index, second input. So that's our new geometry. We're going to grab P, the position vector, and we just want point 0. There's only one point in this geometry. We just brought it in. There's only ever one point. So we just want point 0. And name A, again, we'll just grab that point attribute, name 0. Point B, we'll grab its position B. We're going to grab this from the second input, or the second index rather, so the third input, and we're going to grab it from this random point that we just created here, so RPT. And again, we'll get the name, string and name B equals point to name RPT. So this is basically everything we need to create a line. We've got two positions, and we have the names that we need to assign to each of those points. So let's just scroll down here a little bit. I'm going to give myself a bit more space so we can see a bit more of this. Okay, so I'm going to say int new PTA equals add point, and we're going to add it to 0 to the stream that we're creating. So we're basically making new geometries here. So we're going to add a new point at position A, and we're going to set an attribute on there. That attribute is going to be name. It's going to go onto this new point that we created, and the value is going to be name A. We'll do exactly the same thing for our second point. So we'll just copy this down here. Only this is going to be new point B. We're going to use position B. We're going to use new point B, and we're going to use name B. Now we have our 2 points, and we'll just create the constraint. So to do this, we'll just do new prim is add prim, again to 0. We want a polyline. This just means it's going to be a line as opposed to a closed polygon, as opposed to sort of a planar patch. It's just going to be a line. And we're just going to give it those 2 points. So new PTA, new PTB. This gives us a primitive. To make it a constraint, it needs to have a name and some other properties. So its name we can set easily. We're going to go set prim attribute 0. And this is a special value. It has to be this, just like name. So this is going to be constraint name. And we're going to apply it to new PRM. And you'll remember, it's going to give me an error for a second, but I'll just jump back up. We called this hard constraint hard. We set the data name hard there. So let's go back here. And we're going to call this constraint hard. I'm also going to set another constraint attribute here. I'm going to set constraint type on, again, new PRM. I'm going to set this to all. By default, a hard constraint will let each of the points kind of spin freely on the end. And in fact, I'll go back and I'll toggle this on and off so you can see that. I'm going to set it to all so it's a little bit more rigid. Okay, so by default, that's pretty much all that we really need, but I do still want to set a rest length. And the reason I'm going to do this is it's going to sort of draw things together. It's going to give some dynamics to the simulation here. So let's just create a rest length value, and I'm just going to draw it from sort of a range. So I'm going to use fit 0, 1, which takes a value from 0 to 1, which is exactly what random gives us. So I'll just use that rseed again, and maybe I'll just add some extra bit of information to that. And what kind of lengths do we want? This is totally arbitrary. I'm just going to go from, say, 0.4 to 1.2. So we're just going to pick a random length, and this is what this constraint is going to do. It's going to try to bring these points to be this distance apart. Because you'll remember, we're just picking a random point. It could be any distance away from the existing one. We're going to say, I want you to try to be this distance away. So we'll just set that attribute. This is another one that the simulation will recognize as rest length. And we're going to set it again on new PRM, and we're going to set it to this rest length value I calculated there. Okay, so if we run this, you can see here we actually get a little constraint here. But here's a problem. We're going from piece 01 to piece 01. And part of this is because you can't really trust anything that's going on inside a SOP network, inside a DOP network. Because it's dependent on feedback, even if you sort of scrub through here, it doesn't really know what it's doing. And it's sort of bringing in the current geometry while processing it. You shouldn't generally trust what you see here until you get a much better idea of it. But there is one extra detail here that's definitely going to be a problem. And that's the fact that when we add this first point, it's the only point. There's no geometry over here. And in fact, unless we have a point over here, we don't really have any way to create this, and it's not going to work out nicely because we're going to go here and we're going to do endpoints and it's going to come back with 0. And then we're still going to try to do all of this stuff, and it's not going to be happy with that. So I'm just going to put a little conditional here right after we get our endpoints and say if npts is less than 1, is greater than 0. So only if it's greater than 0 do we do any of the rest of this. I'm going to very quickly pop into the string edit, which you again won't see because it's an extra window, but it's a lot easier to tab over a big chunk here. So bear with me here. We're just going to go to edit string, apply accept. So now you can see all of this stuff is just has just been sort of shifted over. And then we close out at the bottom. So that's all I did there. Okay, so this gives us a new constraint. And now what we want to do is basically the same thing we did over here. When we add a new object, we merge it with the existing stuff, and then we pass that through. So when we add a constraint, we want to merge it with the old constraints. So we'll do another merge over here. I'm going to bring that through, and we're going to merge this in here, and we'll just pipe that back into this switch here. So it's this link here that shows you why you need to have a single network that has 2 outputs. And that's the whole reason that using this basic sort of SOP solver here and going in and doing it at this level doesn't necessarily work quite so well. You could put nulls here and try to reference them from the others, but I find it cleaner to just do all of your work inside one network and then have these alternately reference the outputs from this network. Okay, so you'll see these little errors here. What these are telling you, I'll just read it out for you. It's going to say SOP solver cooked in immediate mode, cached results incorrect. And that's a little bit of what I was telling you before. Even when the simulation claims to be cached, if you change something inside the SOP solver, it's not going to update correctly. It just doesn't quite know. So this is just another reminder to just go and find something and go check, creation frame, etc. Okay, so if we haven't screwed anything up, this should just work now. So let's just run. Okay, so something's gone wrong here. So you can see we are creating constraints and then they're immediately getting removed. They're also being linked somewhere a little bit weird. So something has gone wrong here. Okay, after some quick rummaging around, I realized it was actually a fairly trivial error here. It was hard to know in advance because there was no geometry there, but I should have paid more attention to this little warning here that was saying this is an invalid path. Because here you can see we have relationships, constraint network 1, constraints, geometry. If we go back to our actual spreadsheet here, it's relationships, constraint network 1, constraint network, not constraints, and then geometry. So really I'm just pointing at something that doesn't exist. So every time we merge back in, it's removing everything. It's drawing from effectively a null because this doesn't resolve. So we can fix that very easily. We just go here, and this should be constraint network. Sure enough, that little error goes away. And now if we go back, update everything, and just close this so we have a little more space. We'll run, and there we go. Okay, so these constraints are a little bit big, and they're showing up in kind of a strange way. But by and large, it is doing what we expect. It's just looking a little bit ugly here. These relative positions for the constraints are giving us these kind of funny positions here. We're also noticing, okay, that one is attached. All these funny little hard constraint orbs. Let's just, oops, I didn't mean to freeze that. Let's just make these a little bit smaller so we can see a bit of what's happening here. Let's just make those a lot smaller. So these constraints are being formed, but they're giving us kind of this weird anchor point. And part of the reason for that, I believe, is its sort of rest geometry. Okay, so I had to take a minute there and go back through some of my records and figure out exactly what was going on here. I did manage to sort that out, so actually let me put this back in here. So what did we have going on here? The behavior is that we have these kind of funny, we're getting our constraints, but they're popping up like this. You know, they're not really looking the way that we want them to at all. So for example, let's just step back to one of these. So maybe at 11 here. There we go. So next frame we have that. So we've got a constraint between these two boxes, and that's what this crazy white line here is showing us. But it has these two funny control points, and these we don't really want at all. And so instead of showing us a line between these two boxes, it's actually showing this big complicated arrangement here. Now, if you were to watch the behavior of these two blocks here, they're going to be constrained basically according to the distance they're trying to target. So that part is working, but we want to be able to visualize this a little bit cleaner. We want it to look correct in DOP. So what's going on here? Well, if we dive back inside here and we take a second to look at our geometry. So if we just look at the stuff that we're bringing in, this single packed cube, at the primitive level, if we look at its intrinsics, so these are things that the system calculates for itself that it usually keeps hidden, but we'll use especially this packed full transform quite a lot when you're doing bullet sims. If we take a look at this for the original, this is the identity matrix. So this packed full transform is telling us exactly what's happened to this cube since it started. So nothing has happened to it initially. It hasn't translated, it hasn't rotated, it hasn't scaled, none of that. So we have a nice identity matrix. But if we look at, say, we've got all four of these, so if we look at all the geometry here, so I'll just grab this merge, this new one, again, is still the identity matrix, but all the rest of these have transformed. They're in different positions from where they started. They've moved around a lot. They've rotated, they've translated, they haven't scaled, so none of that sort of ladder column is set up, so scale is all sort of normal. But they've rotated and translated, so there's changes to these. And the reason this is important is because the constraint network understands its constraints, the positions of its constraints in terms of the resting geometry. So you can handle this in a handful of ways. One of them is to sort of try to reverse this transform and figure out where those points should be and make the constraint based on those points. The easier is just to understand that it gets the idea that it starts without any translation. It starts without anything going on. And our cube back here is sitting right at the origin here. It's sitting right at 0, 0. So if we go back to our constraints, and here, where we grabbed the position of our new point and the position of our random point, we can actually do this a lot more simply. We can just say, in fact, I'm just going to get rid of that top line entirely. So let's say we'll redeclare this. So position A, we're just going to put this at the origin. So we're going to put position A at the origin, and we're going to put position B at the origin. And if we do that, and then we sort of run back here, refresh everything, and then run, what you'll see now is that our constraints show up exactly how we expect them. So they're just going between these separate little boxes here. So that's exactly what we want. We want to be able to visualize this as it's happening in DOPs. Now, again, this isn't entirely important because the constraints are still going to behave correctly, even when they're sort of not in the right position. Essentially, the system is just setting or solving constraints that are offset from where we see the geometry. But for debugging, for understanding what the simulation is doing, we really kind of want to have this stuff set up with these boxes here. Okay, so we're just about done. At this point, we've basically got exactly what we wanted to happen. I'm just going to pull out all of this stuff, so the ground plane and the gravity, I'm going to get rid of that. I think this sort of looks nicer when it's just sort of bobbling around. Because before we needed gravity in the ground plane to sort of see anything, to have it behave at all. But now with these constraints, it's going to be kind of pulling and tugging on the overall network, so we can get away with having the least possible things in here. So if we run this now, sure enough, we get new boxes, and they kind of toggle and push each other around in this network, and it all behaves nicely. Everything has sort of new unique names, so it knows how to treat each of these boxes independently. So we've got all our separate pieces there. And if we look at our constraint geometry back over here, I renamed this connet, by the way, just so I didn't have to type as much. You can see that here. So our constraint network is just connet. If we go down into our geometry here, we see we have all of these nice primitives. They're all hard constraints. They've all got sort of their rest length. These variables are things that the system computes itself. So bullet is computing torque, force, distance, and angle. You can use those things to drive, say, deletion of your constraints over time, whatever you like. You can see they each have those two separate points, and they all have the right names and everything. And they're all just sitting right at 0 here. We don't really need any of that data about where those boxes are. Bullet is going to figure that out for the visualization for us. Now, one downside to having Bullet figuring out this visualization here comes from if we actually want to sort of bring this out into a rendering context. So I'm just going to spend the last couple of minutes showing that. Actually, I had one other quick thing I wanted to do that I just realized. So if we look here, we have this constraint type all. I said I was going to show you the difference between having that on versus off, so I'll just do that quickly. So if we watch this, you can see that these boxes are staying relatively rigid. Like they'll spin a little bit, but they're staying essentially, if we just sort of scrub slowly, you can see that this box is not like twirling around on the end of this pivot. And especially the ones that have multiple constraints, they're staying relatively rigidly locked in their orientation. That's because we're not just constraining the position, we're also constraining rotation. That's what constraint type all means. So if I just go back into this position here where we set up the constraint type, if I just comment out that line, so we're not going to constrain type all by default, we're just going to constrain the position. I'll go back here and sort of flag this to resim. So if we run this now, I'll just get through a little bit. You can see, especially here, if you look at this, this box here, you can see that it's twirling around like crazy. Basically, its rotation isn't being constrained. It's more than happy. All of these different sort of boxes on these different intersections are more than happy to just kind of twirl around as they go. So their rotation isn't being constrained. I think it gives it a slightly better look when the rotation is being constrained. It looks a little bit more rigid. So I'm gonna just toggle that back on there. And again, we'll just recache that. And there we go. Okay. So the last thing we're going to do is just look at how we can sort of visualize this outside of our DOP network. So I'm going to use a very simple DOP import here. I'm going to Alt-click the DOP net and just drag it into the DOP network here. And I don't remember exactly what the RBD was called, but I know that there was only one of it, so I'm just going to do star RBD star. That's going to grab that. And the last thing we need to do, we don't want this transform input geometry, we just want the geometry. And in fact, even better, we're just going to fetch the unpack geometry, because we're going to want to unpack this anyway. Yeah, so that's just going to give us those boxes that we had originally. Now we've got all our nice normals. Now, if we want to visualize those constraints, well, you might remember when we grab the constraints here, we just use this object merge. We can just use this framework and this language here. And in fact, because I use an absolute path, I'm just going to grab this whole node here because we're going right from obj, so I don't really have to retype anything. I don't have to remember that whole big long string. So I'll just go back out, paste this here, and that's going to be fetching the constraint network. But what do we have in this network? Well, we don't see any lines here. And in fact, if we turn on our point visualization, we find that everything is just sitting right here. And sure enough, that's because all of our points are at 0. That's where we put them. So there's a bit of a trade-off between being able to visualize your constraints naturally out in SOPs land and having them visualized correctly in the DOP network. But we can handle this pretty easily because this DOP network, this is why I didn't want to unpack it actually. So I'm going to leave this fetch geometry. So we're just going to be grabbing this pack geometry here. We'll unpack it in a second, but I want it to be those 10 packed fragments at the moment. So what we're going to do is just ask these fragments, which each have a name. So we have a fragment named piece 012, for example. This constraint that has piece 012, well, we're just going to move that position to wherever that fragment is, because we know that that's where this constraint is actually pointed to. So we can do that pretty easily. So I'm just going to sort of pipe my points through here, and I'm going to grab these assembled points over here. And then what I want to do with this assembled geometry is basically just find the point that matches the name that this point has. And we can do that with, I'll just call this matchpt, a function called findAttribVal. And this is going to take the geometry, so we want this first input, that second stream. We're going to be looking for a point attribute, and that attribute is called name, and we want to match it to the name of the point that we're dealing with. So we're going to look in this geometry, in this second input stream, for a point attribute called name, and we're going to match it to the name of the point that we're processing on our sort of first input, on stream 0. FindAttribVal will work for integers and strings. It's not going to work for floating points or vectors or anything like that. So it's still pretty powerful. You'll use this quite a lot. It's quite handy. So now that we have the matching point, all we really want to do is find out, okay, given that point, well, what's its position? So vector pose, we'll just say is point 1 p matchpt. So we found the matching point. Now we're grabbing its position, and we're just going to set the position of that point to there. If we turn this on, suddenly we get our whole network exactly where it should be. And we can take this and unpack it, and we get all those boxes there. And we could just sort of merge this together to take a look. And sure enough, we have everything we expect and everything is lining up where we would like. And if we go back, we can just sort of run all of that. All right. So I'm going to call that a part 1 here, I think. We'll come back and look at sort of this fracturing version, where we can generate lots of sort of fractured copies. Oh, it's just trying to cache that whole thing. That's fine. We'll look at this version next time, I think. And it really doesn't involve much beyond what we've done so far. And in fact, in a lot of ways, it's much easier, even though it seems like it might be a little bit more difficult. But I'm going to save that for next time.